I'm Vasiliy Prokhorov from University of South Alabama. We talk about matrix continued fractions, lattice paths, and resolvents of difference operator. This joint work with Abi Lopez Garcia from University of Central Florida and Jacob Kim from University of Alabama. First, we will define two matrices, bounded matrices, and this matrix W is P plus Q plus 1 diagonals, Q super diagonals, main diagonal, and P subdiagonals. And these elements of these matrices are elements of P plus Q plus 1 by infinite sequence of complex numbers. What is important for each diagonal, for example, for main diagonal, upper indexes stay the same. For example, 0, 0, or Q, Q, Q for this super diagonal. Matrix H is subdiagonal of matrix W. Lower index is non-negative integer number. We can see numbers for lower index 0, 1, 2, and also upper index for main diagonal is 0, 0, 0. Now we'll define two operators. First, two-sided difference operator W, and formulas for this operator you can see on the screen. The most important property of this operator, matrix representation of this operator in basis of standard basis M2 L2Z is by infinite banded matrix W. For next slide, we see formulas one-sided difference operator H and standard basis. Matrix representation of this operator is banded matrix H. So we can define systems of resolvent functions for matrix H and system of resolvent functions for matrix W. And now we can talk about lattice paths. Fixed P and Q integer numbers greater equals 1. And we'll define two collections or two sets of lattice paths, Dnij and Pnij, and n number of the steps. I is y coordinate of initial point, j is y coordinate of terminal point, and for each step we have only three possible directions for movements. We can go upwards with maximum displacement of q units. We can go horizontally 1 unit, or downwards with maximum displacement of p units. For collection Dnij, paths never go below x-axis, and for collection Pnij, we don't have such restriction. On the screen, you can see an example of one path from D1813. This is 18 steps. Y coordinate of initial point is 1, and y coordinate of terminal point is 3. And for also, you can see for this path, weight of the path. Okay, and this weight of the path is product of weights for each step. And if you have step E, so weight of the step is number A, top index is K, lower index is M, with M is y coordinate of lowest point, and K is the difference between y coordinates of terminal and initial point on E. And for example, for first step, we have horizontal step, so this means top index is 0 and lower index is 1, because for all points y coordinate equals 1. For next step, we have jump 2 units up, so this means upper index is 2, and then y coordinate equals 1, because y coordinate of the lowest point is 1. And then one more step, this is drop 2 units down, and upper index is -2, because we drop negative 2 units down, and y coordinate of the lowest point is 1. And we can do it for all possible steps. And it's clear that this, if you see this product as a non-commutative product, this product completely determines the path that in given collection. So one more example with path from collection P18 -1, 2. Y coordinate of the first point is -1. Y coordinate of the terminal point is 2 and first 18 steps, and no restrictions for passes. But the maximum displacement upwards is 3 units, Q equals 3, and maximum displacement for downwards is 3 units, and we can see on the screen. So this is 3 steps up maximum, and this is a 3 step down for 1 step. And then for if you fix n, I, and j, so for all these collections, we can define weighted polynomials. And formula for weighted polynomials is sum of weights for each pass from the collection. So we can get nij, wnij. And now if you change n and we'll fix I and j, we'll get generating function for these weighted polynomials. And formulas are written right there. So aijz and wijz. And first theorem, first result, tell us that this generating series is aijz concisely equals resolvent functions for operator H or matrix H, and generate series is for wijz equals resolvent functions for matrix W. So now we're ready to state one of the most important, one of the main results of our work. So let's consider matrix F of Z, Q by P, and elements of this matrix are generating series that corresponds to classes D and Ij. And first theorem is tell us that corresponding matrix can be represented in metric continued fraction. And for the case P equals 1, Q equals 1, this result is famous result of Flageolet and Vinod. So for in year 1995, Callaghan wrote this result in the case when we have vector of resolvent functions of Heisenberg operator, and this corresponds to case P greater equals 1 and Q equals 1. And these formulas we use in pseudo quotient operation matrix A equals 1 over matrix B. We'll talk about this on the next slide or next two slides. Now let's explain these matrices that we can see in the formulas. First row of the matrices has lower index 0, and the next row is matrix with lower index 1 and then 2. And on the next page, you can see formulas for these matrices. And what is interesting, the same formulas we can use not only for this specific matrix, also for next matrix continued fractions that we'll describe in next theorem, except we need to change these elements that is written in the last row or last column or this diagonal. If you look accurately how these elements selected, so we can see lower index is k, and then lower index also for next matrix is k, and this also k. It means to construct these matrices, we need to take k plus first row, and then take elements to the right from the main diagonal. And then this is for alpha k plus matrix. And then we need to take element under from the k plus first column. And these elements can be used for to construction alpha k with minus, and elements on the diagonal intersection of k plus first matrix row with k plus first column give us element from the matrix alpha k. And the same rule we can apply it for the next result. So only instead of matrix H, we will write matrix K. So this is what we see on the next slide. So formulas for matrix continued fractions, and this is a result in 1997, Sorokin and Van Eysenbeem obtained result about expansion of matrix Q by P with elements that are Lorentz series as matrix continued fractions. I use this transformation that's written T and apply these formulas to get this matrix continuous representation. And this matrix continuous representation is translation of the classical algorithm, Euclidean algorithm that corresponds to case P equals 1, Q equals 1, and Jacobi-Perron algorithm for vector vector case when P greater equals 1 and Q equals 1. So now we can state one more result of our work. This result is related to matrix Q by P, and elements of this matrix are generated series for class P and IJ. And we have, again, matrix continuous fraction representation, and the same structure, only matrices that we'll see right there, beta matrices constructed not by matrix H, but matrix K. And now on the next slide, I'll show you how matrix K is defined, but about history of this result, case P equals 1, Q equals 1 is result of Masson and Repka. We obtain this type of representation for for resolvent functions of double-sided Jacobi matrix. So we, with Dr. Lopez Garcia, we obtained 2022 case when P greater equals 1, Q equals 1, and now this theorem is a general case. Yes. And let's see how we can construct matrices B. So, but instead of matrix H, now we'll use matrix K, and almost all elements of matrix K, the same as elements of matrix H, except P by Q submetric located in the top left corner. And we can see formula for these elements with V, I, J, Z are generated series associated with collection of lattice paths that never go above line y equals -1. Now, to understand meaning of this result and to understand extremal properties of convergent of this matrix continuous fractions, let's see first of all case P equals Q and equals 1. We have matrix H is Jacobi matrix with 3 diagonals. Matrix W is two-sided matrix with 3 diagonals. So this formula is a result related V naught for scalar case P equals 1 and Q equals 1. This is formula for generating series of weighted polynomials of lattice passes. This is formula of Masson and Repka. And now let's do n by n principal truncation of matrix H. And using this truncation, we'll get matrix H. So using this truncation, we'll get matrix Hn, and we can write resilient function for this matrix Hn. It's easy to see this matrix, this resilient function is a rational function with denominator is characteristic polynomial and numerator is polynomial degree at most n-1. And this slide is important because it explains us extremal properties of matrix continued fractions or continued fractions. And we have similar properties for matrix continued fractions. So this is generating series. This is a resolvent for principal truncation. What is important first, this truncation matrix, this resolvent function is convergent of series A00. So this means this is convergent, and also this rational function is Padé approximation of Laurent series A00. So it means in this case, so this rational function has 2n coefficients the same as power series A00. So now let's consider a general case. We need to do n by n truncation, and then we construct characteristic polynomial, and then we can write formulas for resolvent functions of this truncation. We'll get rational functions, and what we'll get fundamentally is two properties, and this analogs of the properties we have for classical case P equals 1 and Q equals 1. So if you construct by resonance of truncation this matrix of rational functions, resonance, so first of this matrix Rn is convergent for matrix continuous fractions that we define in theorem 2. And second, this matrix of rational function is matrix of Padé approximants for matrix f of z. So this means if you fix I and j, and one of the properties, if you fix I and j, and n goes to infinity, this rational function Ri and j has as many as possible the same coefficient as Aij, and number of common coefficients is with n approaches infinity, grows, increases with asymptotic n times 1 over p plus 1 over q. So now the last slide, and we can see this is article, this is paper that we submitted in Mass Archive. In this paper, you can find more references and more details of our results. Thank you.